Yeah, we are able to hear you, sir.
Yeah, for this impedance control, we will be using the impedance related formula, which we discussed in the previous session. So basically, these three aspects of the layout designing are checked. Okay, during whenever you perform DRC validation, these three constraints are checked. Okay, the first one is geometric constraint, second one is electrical rule, and the third one is manufacturability. Okay, manufacturability is also checked during the DRC validation. So on geometric constraint, minimum trace width, I already told you between two copper tracks, the minimum clearance should be at least 0.15 mm. It can be even more. Okay, even if you put 2 mm or 5 mm, that's fine, but it should be at least minimum of 0.15 mm. If it is less than 0.15 mm, that will cause a geometric constraint DRC error. So the minimum clearance between two copper traces, you are not following it, you are violating it. Okay, that's why it will throw an error, DRC error, because you are not following the geometric constraints. Okay, so the second one is electrical rule, where we are having power rails and power rails. So if VCC or ground get overlapped, the entire charge from VCC will get discharged into the ground. So that will cause other components will have lack of current charge. Okay. So and the third one is manufacturability. Yeah. Third one is manufacturability. So in this manufacturability, we will be having shoulder mask clearances, drill hole sizes, and board edges proximity. Okay, we will discuss about these in detail in the upcoming session. Actually, it's like a overview. So there is separate curriculum for DRC where we'll be learning. So just like as I told you, between two copper traces, the minimum clearance is 0.15 mm. So this is just one rule among hundreds and thousands of rules. This is just one rule. So like this, we are having so many rules. So all these rules cannot be explained in this curriculum because we are just only focusing on the to how to we are just like introducing the PCB designing to all new candidates. Okay, so it is one DRC rule among hundreds and thousands of DRCs. There are for different components there are different clearance rules, right? So between copper traces it's 0.15 mm. That is the minimum spacing, minimum clearance. So why DRC matters in PCB design? The complexity of modern PCBs featuring nowadays we are having multi-layered PCBs also. And I already told you that there is something called 50 ohm rule. Okay, we derived a impedance formula. Okay, so many of the, if you want to design high speed data transmission activities, the impedance of the copper traces should be 50 ohm. Okay, so it's, I already gave you assignment. If you not yet done any research why 50 ohm, please do a research why 50 ohm is chosen as the standard impedance, okay, for high speed data transmission rails or else high speed signal copper traces. Okay, yeah. So the complexity of modern PCBs featuring multi-layer boards, high speed signals and dense component placement, so makes manual verification nearly impossible. Okay, everything you cannot manually verify. Yeah, so everything cannot be manually verified. So that's why manual verification is nearly impossible, because as day by day, as day passing, as technology getting increased, the components are placed more denser. Okay, because of the space considerations. Yeah. So because of the space considerations, as technology is increasing day by day, so everyone prefers to, all companies preferring to place the components more denser. Okay. So there is something called a dense ratio. Okay. So it's actually a new term, dense ratio. So it is actually, this term is used in IC design, chip design, integrated circuit design, in when you are working on floor planning. So right now we are designing PCB design, right? Similarly, we have another course called IC design, chip design, integrated circuit design. So in IC design, there is one, just like we are having multiple processes, multiple steps in making a PCB. In IC design, we are having one procedure called floor planning. Okay. So in floor planning of IC, there is something called a dense ratio. So this dense ratio is used to determine how closely standard cells are packed. Okay, this is completely different terminology dealing with. So here also dense ratio means how close the components are placed in a PCB. Okay, but despite you are placing the components more closer, still you need to follow the DRCs. Between one component and another component, there will be minimum clearance rule. So following those minimum clearance rule, you can. But see, if you want to make it even more denser, you can do it, but it's not allowed, because if you want to make it even more denser, it will violate the DRCs. Okay, design rule check. Those rules and regulation it will be violating, which will cause a DRC validation. During we are performing DRC validation, it will throw an error. So you can pack as much as closure as you want, but still you need to abide DRC rules. Just like as I told before, few people joined little bit late. So for them, I'm just repeating. Basically, in DRC check, when DRC is performed, three main aspects are verified. Okay, the first one is geometric constant, second one is electrical rules, third one is manufacturability. These three parameters are verified during DRC validation. Geometric constraints refers to different geometric placement. Okay, minimum clearance rules between two different components, all these things come under geometric constraint. Between two copper traces, the minimum clearance is 0.15 mm. If it is less than 0.15 mm, it will immediately, whenever you perform DRC check, it will immediately throw an error. Okay, no sooner you started performing DRC, as soon as it started verifying the copper traces, the particular trace, it will immediately throw an error that the minimum spacing is not, you are violating the minimum spacing between copper traces. Okay, so geometric constant, electric rules and manufacturability. So why DRC matters in PCB design? As technology is increasing, we are seeing multi-layered PCBs, high-speed signal data transmission related thing, 50 ohm rule. We are about coming to the impedance. So the placement, the component placement in a PCB getting more denser and more closer. Okay, more trying to fit entire things in a small place. But still you need to follow DRCs. Why DRCs? Because DRCs are there. Those are based on multiple experimentations and different things, those DRCs are proposed. So if you place two copper traces are, if you just put it more closer, even less than 0.15 mm. So during actual manufacturing, there is a probability because manufacturing, see, not only design precision is enough. Those who are manufacturing the PCBs, they also have some machinery and equipment. So for that also there is a precision. So all machines may not have high precision and accuracy. There is always some limitations to the hardware. Okay, machinery tools. So if it is less than 0.15 mm, there is a more possibility that these two copper traces, despite in your design, those two copper traces are not overlapping each other. But at the time of actual manufacturing, due to the hardware machinery limitations or else due to lack of accuracy or any other reason, there is a high probability for these both copper traces getting overlapped with each other, which will cause a geometric. See, actually, while you are performing, that's why DRC validation is introduced. So they have already clearly in the DRCs they proposed what should be the minimum spacing. All these rules are already proposed. So just to follow DRCs, so even you manufacture PCB, no, nothing will happen because those minimum spacings are proposed by keeping different machinery equipments in consideration. Okay, so always DRCs are safer to follow, but at certain times we need to, let's say, at power rail sometimes we usually put 5 mm as spacing, not 0.15 sometimes. Let's say you put 3 mm. So yeah, so some depending upon the circumstances, depending upon the cases, we may slightly deviate from DRC, but basically we are not violating. So putting a little bit more spacing is not considered as violating the DRC. Okay. So with the DRCs, these four things are possible. First one is early error detection. Identifies issues like short circuits or misaligned wires during the design phase, reducing prototype iterations. So without DRC, let's say you build some PCB and you made it fabricated with the help of some fabrication unit like JLC PCB or else something else, and you got a PCB and at the time of testing it's not working. So maybe it could be due to some short circuit or whatever. Maybe there might be different kinds of possibilities, right? So but if you are having DRC, you can detect the errors early during the design phase itself. You can detect, so early error detection. And you can also reduce prototype iteration, because if first PCB is failed, again you need to do one more design and again you need to get it fabricated. So these prototype iterations are also reduced. And the second one is cost efficiency. Fixing errors before fabrication avoids expensive rework, isn't it? That's a fundamental fact. Okay. Next one is, for instance, correcting a trace with violation in software is far cheaper than scrapping a batch of faulty boards. So fixing error, prevention is better than cure. In other words, fixing error before fabrication avoids expensive rework. And the third one is improved manufacturability. So ensures that design, whatever the design that you are doing, it aligns with the manufacturer's capabilities. So yeah. And the next one is enhanced reliability. So these DRCs are proposed in such a way that the PCB that you are designing is will have high reliability. It could be signal integrity or it could be power distribution, right? So for, let's say you're working on critical projects like automotive related, EV vehicles, so or else medical related electronics. So where failure is not an option. In medical electronics, failure is not an option, right? So it enhances the reliability. Okay, for power distribution related things also, many DRC rules are proposed. So if you follow all those DRCs while in the time of implementing power supply, input power supply to a PCB, if you follow all DRCs, then there would be no issues, no power related failure. Okay, yeah, it enhances the reliability. So coming to the common PCB layout mistakes, DRCs helps avoid. First one is insufficient trace clearance. I already told you the minimum clearance between two copper traces is 0.15 mm, which is already mentioned over here. I think so. Yeah, here we can find it. So one of the most frequent errors in PCB design is inadequate spacing between conductive elements like traces, or wires. So insufficient clearance can cause short circuits, especially in high voltage or high density designs. For example, a clearance of less than 0.15 mm between traces in a 5-volt circuit may lead to uh, arcing or else shoulder bridging during assembly. Okay. And the DRC solution. Set clearance rules based on the board's voltage. So the minimum clearance between two copper traces is not constant, not same for all the things. So depending upon the voltage, the clearance varies. For 5 voltage, it's a 0.15. For 3 volt, it would be different. So for different voltages, minimum clearance would be different things. Okay. So if you are working on low voltage, let's say if you're working on 3.3 volt, then you can put even less than, something like 0.2 would be sufficient. Okay. Sorry, not 0.2, less than 0.15 mm would be sufficient, something like a 0.1, but it is not advisable. Okay. So if you put 0.1, that is very small. So for high voltages, for higher voltages you can put 0.5 mm. I already told you 0.5 mm. Just I gave an example earlier. Usually we put 0.5 mm for high voltages. So for low voltages, usually it is less than 0.2 mm. Okay, usually it is less than 0.2 mm. Depends on the voltage. So, but it should not be less than 0.15 mm. Okay, so it should not be less than 0.15 mm. So you cannot put 0.1 actually, because if you put 0.1, that would lead a DRC error because it is less than 0.15 mm. It can be less than 2. Okay, so the clearance between two copper traces, it can be less than 2 mm, but it is advisable to put the minimum enforcement as 2 mm for low voltages. Okay, if you put 0.2, it won't throw an error. Okay, if you put 0.17 also, it doesn't throw an error because the minimum is 0.15. Okay, but it is advisable to put minimum enforcement of 0.2 mm. Okay, so never put the minimum clearance between two copper traces less than 0.15 mm. And incorrect to trace widths, we all see, those who don't know the copper width, how to determine the trace width, those candidates will face this issue. But right now there is no chance for you to face these kind of issues because you already very well aware about how to determine the minimum, how to determine the width of the copper traces. Already we are having two PPTs on that, right? We discussed about it very well. So in detail information about these particular things, so you need to opt in for higher courses. As of now, this we are giving you the basic overview. Okay. And coming to misaligned or improperly sized vias. So you need to orient it in properly. Okay. So for this also there would be a minimum spacing rule. For example, a via with a drill diameter smaller than 0.3 mm may be unmanufacturable by some fabricators, leading to open circuits. So you know about vias, right? So vias are there to connect multiple layers. Okay. So if you want to switch, if you, let's say you're having a copper trace in the upper surface, top copper layer, and you want that same connection, the same signal to be transmitted to the bottom copper layer, then via is used. We already discussed the types of vias, buried via, isn't it? Uh, and one more thing. So one via starts from, actually it's visible from the external surface, and buried via, it is not visible from external surface. It stays inside in the internal layers only. Okay. Blind via is visible from the external layer. From the top layer you can see the blind via. But whereas buried via, it stays only in the internal layer. So the via size, if it is smaller than 0.3 mm, certain manufacturers can fabricate it. Okay, if they are having high precision and high accuracy equipment machinery, but few fabricators may not be able to fabricate it. Okay, so if the manufacturer is unable to fabricate that via, so if he leaves it like that only, then it will result in a open circuit because the circuit is not getting closed, right? The connection from the top copper layer and the bottom copper layer is not getting closed. It leads in an open layer. It's like an open circuit, not open layer, open circuit. So your PCB will definitely not work. So that's why make sure that the drill diameter should not be smaller than 0.3. So from this we can understand the minimum radius of any drill diameter should not be less than, yes, should not be less than 0.15 mm. So radius, the minimum drill radius of any wire should not be less than 0.15 mm. Similarly, the minimum spacing between any two copper traces should not be less than 0.15 mm. You can put for low voltages, you can put 0.2 mm. For high voltages, you can put 0.5 mm. But never put the minimum clearance between copper traces less than 0.15 mm. Okay. So similarly, drill diameter, the minimum drill diameter which is suitable for manufacturing is 0.3, or else the drill radius is 0.15. Okay. So never put less than 0.15 as radius, or else 0.3 as the diameter. And next, inadequate shoulder mask clearance. I hope my screen is visible. My screen is visible, right? Yeah.
Yes.
And coming to the next one, inadequate shoulder mask clearance. Shoulder mask clearance is the gap between the shoulder mask and the exposed pads or traces. Insufficient clearance, example less than 0.1 mm, can cause shoulder bridging during assembly. So yesterday we discussed something called tented wires and non-tented wire. So how many of you remember about tented wire and non-tented wire? Just in the previous session we discussed difference between, yes. Can someone just explain me? Unmute yourself and explain me what's the difference between tented wire and non-tented wire. We discussed with the help of images as well. There are two types
Uh,
of wire based on shoulder. Yeah,
yeah, tension wire is nothing but is a normal wire, but the upper layer is covered by the solder mask. And non-tinted wires is as usual wire.
right. Perfect. So in tented wire, we will be having a shoulder mask covered on the top of it, right? So even during that, you need to make sure that the gap, okay, you need to follow this clearance rule. Okay. So if it's less than 0.1 mm, it will cause an error. Okay? Insufficient clearance. So shoulder mask clearance is the gap between the shoulder mask and the exposed pads. It should not be less than 0.1 mm. Yeah. So like that, we are having many, so many kind of common errors, but we are just listing out most commonly, you know, most common errors that everyone usually undergoes these, or else most people usually do these mistakes. Okay. So the first one we discussed is insufficient trace clearance, where we discussed to put at least 0.2 mm for low voltage, like an enforcement, and 0.5 mm for higher voltage, but never put less than 0.15 mm. And next, coming to the uh, incorrect trace widths. For this, we are having an excellent formula. I is equal to K into delta T to the power of 0.44 into A to the power of 0.725. If you follow that formula, nothing will, no, you know, you will never undergo these, you will be never doing these kind of mistake. There is no chance for the DRC validator to throw incorrect trace with error. There is no chance for that. If you follow that formula where K is equal to 0.048 for external layer and 0.024 for internal layer. If you follow that formula, you will never get DRC error on this specific thing, incorrect track width. Next one is misaligned or improperly sized wires. So it should have a minimum diameter of 0.3 mm for drill holes, or minimum radius 0.15. And inadequate shoulder mask clearance. The minimum clearance is 0.1 mm for to apply the shoulder mask. So next one, board edge proximity rules. Placing copper features too close to the board edge within 0.5 mm can result in shorts during fabrication. So always we need to make sure that the copper placement should not be too close to the board edges. Never place copper traces too close to the board edges. So just to maintain a gap of 0.5 mm between the copper traces and the edges. So from all the sides, okay, from we are having a PCB, right? So it is having total four sides, okay. From all four sides, maintain 0.5 mm clearance to place any kind of copper traces, okay. So that is the board edge proximity rule. And next one is signal integrity violation. So in signal integrity violation, we are having different kinds of impedances. Here impedance will come into the picture. So there are different impedance rule like 100 ohm impedance, 50 ohm impedance. So like that there are different rules. So we discussed the impedance formula and we discussed one more thing like for high speed signal integrity, okay, for high speed signal integrity and high speed data transmission. Commonly every manufacturer follows 50 ohm as the standard impedance. Okay, copper traces should have 50 ohm as the impedance. Then data transmission would be fast. So that's the assignment for you. Why 50 ohm? And there are 100 ohm rule is also there. Explore about 50 ohm and 100 ohm rule. In the next session, we'll discuss about 50 ohm and 100 ohm rule. Yeah. So this is all is theoretical. That's not necessary right now. So this is today's session. So from today's session, we understand. I will be summarizing few things. So the first thing is three main things are checked when you perform DRC. Three main things are checked. First one is, yeah. Can someone tell me what is the first one? What is the first one? Second and third. Okay. Okay. Someone tell me first one and another someone tell me second one and another and one more person tell me any three members. What's the first one? Three main things are verified during DRC. So someone need to respond or else I will also stay like this only in the meet. Unless you respond, I will stay like this only. Yeah. Anyone, you can directly unmute yourself.
So, like the minimum distance between two traces must be 0.15. If it's high voltage, it should be 0.5.
Okay. I'm not asking directly about the rule. Okay. So I told you there are three main things, right? Which are verified: geometric constraint, electric rule, and manufacturability. Those are the examples commonly performed mistakes. Okay. For that, I gave you few examples. But the three main things which are verified during DRC are geometric constraint, electrical rules, and manufacturability. Okay. Whatever you are saying, the minimum clearance, all these come under geometric constraint. So drill holes, the minimum diameter 0.3 mm for drill holes. All these come under geometric constraint. Okay, and impedance related, signal integrity related, those come under electrical rules. And whatever the 0.1 mm clearance for shoulder mask, okay, those come under and board edge rule. So for board edge, the minimum clearance is 0.5 mm from the edges of the board. If you want to place any kind of copper truss, it should be at least 0.5 mm away from all the edges of the board. That comes under the manufacturability. Okay. So these are the three types of DRC checks performed. When you are validating DRC, first it checks for geometric, electrical rules, and manufacturability. These three are verified. Yeah. So hope today's session is clear. So this is today's session. And I'm Hemant, your expert mentor from Suchana. Signing off. Bye bye. So in the next few minutes, I'll be taking next 4 minutes. I'll be taking questions from you. If you have any questions, you can share your question. You can unmute yourself or you can post in the chat box. Yeah, I think no more questions. So thank you for joining today's session. This is Hemant, your expert mentor from Suchana, and signing off. Bye bye.